Uh, Good evening. We're going to talk today about vector analysis part 2. We're going to talk about differential calculus. So let's recall what calculus is to begin with. Suppose you have this curve which is indicated by this, and we would like to find out the tangent at say x is equal to phi. By tangent we mean simply a line that's glancing at this point, hitting that point in a glancing fashion at x is equal to phi. And to do that, what we will do is we will chop this curve into finer and finer parts, right? So we can divide this curve into some parts, so that as we keep dividing, you don't see this curve kind of thing anymore, but you see that it becomes more and more like a line. So you see that if I go from, instead of 0 to 5, if I reduce that to 2.5 to 5, you see that it looks more like a line, but you can still see some bend, some curve here. But if I zoom in even further, for example, if I go only from 4.7 to 5 within this region, you can see that it looks like a line here, right? So we are approximating this by chopping it into finer and finer parts, and that is what we call as derivative. The thing to note here is that we are reducing delta x, and as delta x tends to 0, we are asking what is the value of delta y over delta x. The thing to note here is that when we say delta x is going to 0, we are not really completing this limit. This is a mental construct. It's a being of reason. We are acting as if this limit is completed, but it is not really complete, in the sense that a line is potentially divisible into infinitesimal points, but you are not actually dividing it into infinitesimal points. So, and this is very important to note. So let's take a simple example, right? Let's take a simple example of a single variable function, y of x is equal to x squared. Then, we can find out what is the derivative here. So if you want to look at dy by dx, then that is limit delta x going to 0, and y of x plus delta x minus y of x divided by delta x, right? So y of x plus delta x is, what we are saying is, this is delta y, right? So that y of x plus delta x is x plus delta x whole squared minus x squared by delta x in the limit delta x goes to 0. And if you do the math, you can see that limit delta x tends to 0, you would get 2x plus delta x, right? Because when you write this, expand this into x squared plus delta x squared plus 2x delta x, right? The x squares get cancelled out, and the delta x in the denominator cancels out the square factor, and so we have this. So if we act as if the limit is completed, then delta x is 0, so the derivative would be 2x, right? Now here we talk about a single function. So instead of single variable function, what if we have a multivariable function, right? For example, if I look at a surface, if I look at an xy plane, and I map out the temperature, let's say, or height at each point, right? Then what I have is temperature at xy, each point here. So this is a scalar field, in the sense that I'm taking each point in the xy plane and assigning this point, each point, number, right? And so that's how we have this scalar field. We can also do it for a volume. For example, if you measure temperature on a volume everywhere, you can have a 3-variable function, u of x, y, z. Now, if you want to know dt here, then this dt is the derivative along x direction, or x, not direction, because this is a scalar field, the derivative in x, and the derivative in y, and derivative in z, right? So now what we are going to do is we are going to take this and we are going to split this into two vectors. This is a number, note you that this is a number, And we have seen that the dot product in the last lecture, we have seen that if I have dot product of two vectors, that gives you a number 2. So what we are going to do is we are going to use this to convert it into two vectors. And what you have to note here, again, I would like to remind you that there are vectors by analogy, right? In the sense that some vectors are denoting magnitude and direction in quality, and that you need to bear in mind. It will come up. It's just a reminder here. So we're going to take this and split it into two vectors by writing this as dou t by dou x along x plus dou t by dou y along y plus dou t by dou z along z, and a dot product with dxx plus dyy plus dzz. And we're going to call this dl. And this, we are going to split this further into an operator. So we are going to take all these derivatives and club them together, and we are going to call that as an operator, as an inverted del operator, right? The gradient operator. We are going to give it an arrow on top because you see it's a vector, and this is operating on t. It is not multiplying t. It's operating on t. T is a scalar field here. It's operating on a scalar field, takes scalar field as an input and spits out a vector field as an output. So we're taking the scalar field t and generating a vector field. So this is an operator, right? So vector operator dot dl. So I can write this as gradient of t dot dl. So this, the inverted del operator acting on the scalar field, is what we call as gradient. So here, two things to note: the gradient is an operator. It is not multiplying. It is acting on a scalar field and producing a vector out of it, right? So you are taking a scalar field and producing a vector. So if you say vector, every vector has magnitude and direction, even if it is by analogy, in terms of, even if you're looking at equality, even in terms of that analogy, it has a magnitude and direction, like how we have seen in the last lecture with respect to brightness patterns over the surface of a lake. Right? We directed the arrows along the direction of increase in brightness. So what is the direction of this gradient is what we would like to find out. So to do that, let's see that dt is equal to, we wrote it as gradient of t dl. So we know that a dot product a dot b, dot product means projecting one vector upon another. So if I have a vector a, by doing dot product with vector b, I'm projecting this vector a here. This length is a dot b, so I'm projecting it onto b. And because this is the adjacent side, if this angle is theta, if this is the adjacent side, then I have, I can write this a dot b as simply as magnitude of a times magnitude of b times cosine theta. So then I can write this gradient as gradient of t dl cosine theta. So now if I fix dl and ask along which direction would I find maximum increase in the temperature, for example, taking T as temperature, then the answer is, along which this product is maximum, and this cosine theta is the maximum value is 1, and that happens when theta is equal to 0. That means when dl is pointing along the direction of the gradient, we get maximum change, maximum increase. So this gradient of t, the direction of this gradient, it's a vector, right? We're taking a scalar field, temperature for example here, and producing a vector field out of it by having the gradient act upon it. And the direction of this gradient is pointing along the direction of maximum increase, right? And the magnitude of this gradient then gives you the rate of increase. how much it is increasing, or like how we have seen in the previous example, the slope of the tangent is changing. So that's what the gradient vector is. Its direction is telling you the direction of maximum increase, and its magnitude is telling you the rate of increase. And the thing to note here is that this inverted delta is an operator that's acting upon a scalar field to give you a vector field. Now let's look at a simple pictorial representation to understand the gradient better. What you see here in this plot is we are looking at the height of a mountain. So z is a function of xy. At each xy point, we're looking at a height and plotting this. So you can see a two-dimensional contour map of the same thing on the right-hand side. Right. So, for example, if you look at these black lines are contours that are connecting. These are connecting the lines that have the points that have the same height. And so, for most of those functions, these are closed loops. If you think about it, for most of the functions, they should be closed loops. And so we have these closed loops. And what we would like to find out then is, the direction along which there is maximum increase. So if we are at this point, shown by the red dot, then the direction of maximum increase is going up. We are going this way. Now, if you look at this from a two-dimensional perspective, right, just from an xy plane, you see that gradient is pointing this way. That means if you think about the same picture, the gradient pointing along this way, that means you're going up the hill. You're going uphill. So the gradient is pointing in the direction of maximum increase, and its magnitude gives you the rate of increase. Right. So that's how we introduce the del operator. It's a vector operator that acts upon a scalar field and produces a vector field. Right. We're going to use this gradient a lot. Okay. So now let's look at something else. It's called the divergence. So we have looked at dot product. So now if I have a vector A, let's say that is AXX, AYY, and AZZ, if I have a vector, I'm going to find out the divergence by taking a dot product between this thing, the del operator and the vector A. Right. So as you can see, this dot product, the answer it should indicate is a scalar or a number. Correct. So then I can write this as the del operator is dou by dou x, dou by dou y, plus dou by dou z, right? And the dot product with AXX plus AYY plus AZZ. So instead of writing these things every time, we can use Einstein's summation convention. So what that means is I can write this entire thing as dou by dou xi cap. So I repeat I. So that means I sum over I. So I act as if there is a sigma sign here that's going from I is equal to 1 to 3, and I is equal to 1 means x, I is equal to 2 means y, I is equal to 3 means z. Right. So that's Einstein's summation convention. So I can erase this sum, because if an index is repeated, we don't need to write the summation sign. It is summed over. Right. So then we have this dotted with AI AXI dot XI, right? So then what we get is simply dou AX over dou X, dou AY over dou Y, plus dou AZ by dou Z, right? That's what our divergence gives you. The name divergence basically implies literally how the field is diverging out, how the field is spreading out. For example, here you can see some simple examples. Here you see, if you look at the arrows, they're going out. There's a flow outwards. Right? There is a flow that's going out. Here you see a flow coming in. So if I were to draw a circle or a sphere here, then I can see there is more going out than coming in. So there is a net outward flow, right? Net outward flow. So this is like a source. So as if it's like a water faucet, for example, right? It is spreading out. There is an outward flow. Whereas here you see that there is, if I take a circle, it's opposite because the arrows are pointing in the opposite direction. There is an inward flow. So this acts like a drain. So divergence tells you whether there is a net flow out or net flow in. So for this, divergence would be greater than 0. For this, divergence would be less than 0. But for something like this, if I take this region, right, one arrow is going out, one arrow is coming in, one going out, another coming in. So net overall divergence, it has is 0. So you can, using divergence, you can look at you can look at how the flow is happening. So you may think that, okay, if we have this graphical representation and we can see whether the flow is diverging out or not, it's so clear from these pictures. Why do we need to have these operators? Because sometimes these what you see could be very misleading. And to see that, let's do a couple of examples here. So first, let's take a vector field, one vector field. So here we're going to do an example to see what divergence is. So we are going to take the divergence of a vector field that looks like this: x, x, y, y, z, z. Right. So let's look at how this vector field looks like if I so let me open this vector field plotter. So so here we can plot that. Just the page. So we're going to plot that vector fields and see how they look like. So I'm going to plot. I have x, x, y, y, and z, z. That's the vector field I want to plot. So now you can see, right, the arrows are pointing outwards, right? So you know that there should be some net divergence, right? If you look at from here, you see that arrows are pointing out. You can move this, right? And you can even move it in dimensions, right? So you can see the net arrows are pointing outwards, so there should be net vector field, right? So let's go back to the PowerPoint here and see how that should look like. We're looking at the divergence. The example we're looking at is divergence of vector xx plus yy plus zz. So if I want to calculate the divergence of this, then I do dou x by x plus dou y by y plus dou z dot product with xx, yy, zz. As you can clearly see, this dou by dou x, when it multiplies with this, you get dou x by x is 1. For this, you get another 1. For this, you get another 1. So now you get 3. Right? So this is greater than 0, the divergence. So it is flowing outward, like how we have seen. Now let's take another vector field that's very similar to A. We'll modify it only a little bit. Very similar to A. We'll modify it a little bit. Let's do it on the next page. So we have looked at A, which has a positive divergence, and I'm going to create another vector field B, right? That is simply same as vector field A, but in the denominator you have x squared plus y squared plus z squared 3 by 2. So now let's look how this vector field looks like when we plot it, the vector field B. For this, we got gradient of A is equal to 3, and from what we have seen, it was very evident that what we looked at was very evident from the graph here previously. So let's plot the new vector field. So we have a denominator here. We have x squared plus y squared plus z squared whole to the power 3 by 2, right? oops, okay, x by x square plus y square plus z square whole to the power 3 divided by 2. I can kind of copy this and paste this here, and this changes to y. Okay, let me just check once. Copy this now. Sorry for the trouble there, it's a little confusing copying here. What I'm trying to do here anyway is I'm trying to plot the vector field B that I had shown you, so that you can see how graphs could sometimes be very misleading, right? So now, okay, so now you can see the vector field here for vector B, right? You can see that there is still net outward flow in the sense of, no, I should not say outward flow. You can still see that these arrows are still pointing outwards, right? So by looking at this, you might think that there is a net outward flow, but you see that the length of arrows is decreasing as you go out. Right? The length of the arrows, the net outward flow is not increasing like in the previous one. It is decreasing as you go outwards. So now let's actually calculate. Go back to the PowerPoint and actually calculate the divergence of this thing. So we have then the divergence of B would be dou by dou x of x divided by x squared plus y squared plus z squared whole to the power 3 by 2 plus dou by dou y of y divided by, because this is going to be xx yy plus zz divided by x squared plus y squared plus z squared 3 by 2. So when we do the dot product with the operator, we get the x term here, y term here. I hope you're following me. If you don't follow me, you can ask me questions on the Zoom session if you're not understanding this. And if you can't attend the Zoom session, you can email me, or I'm going to record the Zoom sessions and you can watch me answer questions there. So now you can use a simple quotient rule. For example, if you look at this part, you can use simple quotient rule, right? So the derivative of this would be simply x squared plus y squared plus z squared 3 by 2 minus x times the derivative of the denominator. That would be, so I'm using the quotient rule, so d by dx of f over g would be equal to f prime g minus f g prime by g squared, where the prime indicates derivative, right? So then I have x, and I'm going to take a derivative of this, so I'm going to get 3 by 2 x squared plus y squared plus z squared 3 by 2 minus 1 is going to give me half, right? And then I have to do x squared, so I get 2x, right? And then divided by g squared, that is x squared plus y squared plus z squared whole to the power 3 by 2. We're just going to do it for this one. For the rest of them, it's just substituting x with y or z, right? So then I can write this as the 2's cancel out and I get 3x squared. So I can pull out x squared plus y squared. Oh, this is squared, so this whole thing should be squared because it is g squared. So now I'm going to pull out a factor of half here. So so then I'm going to pull out x squared plus y squared plus z squared to the power 3 by 2 here. Then I'm going to get 1 minus I will get 3x squared, right? And this is pulled out, so I have this much divided by x squared plus y squared plus z squared, right? I'm pulling out 3 by 2 from here, so I'm pulling out half rather. So I have x squared plus y squared plus z squared whole to the power 1 left out there. So then I get this is cube, right? Then I have simply here the x squared gives you the 2x squared here. So I get y squared plus z squared minus 2x squared divided by x squared plus y squared plus z squared whole to the power 5 by 2. Right. So that's what I'm going to get for doing the derivative of the first one, right? And then we can check this out very quickly using the derivative calculator, just in the interest of time. So we can use derivative calculator. Like the one from Symbolab. So do by do x divided by x squared plus y squared plus z squared y squared plus z squared whole to the power 3 by 2. Right, and here we want to have 2 by 2x. Right, and then so that's right. So what we got is right, y squared plus z squared minus 2x squared. This was just a quick check because my difference has been rusted for a few days. So we get this, right? So then I can write it on the next page, right? So then I would get gradient of b vector, that's what we are doing, to be minus 2x squared plus y squared plus z squared divided by x squared plus y squared z squared whole to the power 5 by 2. This is for the part where you have x, and the part for y would be similarly minus 2y squared plus x squared plus z squared and x squared plus y squared plus z squared whole to the power 5 by 2. For the part where there is z, you would have minus 2z squared plus x squared plus y squared divided by the same denominator. So we are going to just simply add up the numerators, right? So the denominator is common, x squared plus y squared plus z squared to the power 5 by 2. I have here minus 2x squared plus y squared plus z squared minus 2y squared plus x squared plus z squared. You can see where this is going probably, but bear with me for a minute here. So then I have one positive y squared, another positive y squared cancels with negative 2y squared. One positive x squared, one positive x squared cancels with this. Same thing with z squared, cancels out. So you get overall divergence to be 0. So what we did here is that we have balanced out the divergence. So we started with this x plus y plus z vector, where when we looked at the vector field, the graph of it, we saw that there was a net divergence going outward. Then we modified it a little bit to vector b by dividing it with this. Then I did all this differentiation using the quotient rule, and then just for the sake of clarity, I checked it with Symbolab. You can do that with Mathematica as well if you like, but it always is a good point to know how to work these out by hand, just in case you are lost in space and you don't have a calculator. But in any case, what we're doing with this denominator is that we are balancing out the flow. So when we look at the graph, when we look at the plot, like how we have seen here, we plotted the 3D vector field here in 3D, you still see that the vectors are pointing out, but the net divergence is 0. That is because the amount of flow coming in is balanced out, because the length of the arrow is decreasing, as you see. So there may be more coming in, but you know that it is balanced in such a way that overall whatever is coming in is cancelled out by whatever is going out. So there is no net divergence. Graphically, from graphics point of view, from a plot point of view, you can see that arrows are pointing outwards. So just because arrows are pointing outwards, it doesn't mean that necessarily the field should have a divergence, right? So now if you actually reduce this to 2 dimensions, so let's put 0 here, right? And if you just reduce this to 2 dimensions, then you will see a different result again. So if I do this by 2 dimensions, so I have just simply x squared plus y squared, right? And y divided by same thing, x squared plus y squared, right? And here you can see again that this is in 2 dimensions. If you calculate the divergence for this 2-dimensional field, you will see that it has a net divergence, or even if you have to the power 3 by 2 and to the power 3 by 2, it should still have a divergence. So let's go back to the PowerPoint. So what I'm trying to make here is to make here clear is that don't be fooled by how the graph looks like, right? So it may look like the graph has these outward arrows. That doesn't mean that there is a positive divergence, or divergence is not 0. Depends upon how the arrows are. So when like I said, when we're looking at any field, you're taking an area and seeing how much is coming in and how much is going out, whether there's an outward flow or inward flow, or there is no flow, right? So that's what our divergence is. On the homework, the next homework, you will have to calculate the divergence for x y divided by x squared y squared to the power 3 by 2. You don't have to note it down. It will be on homework 2, right? And very similar to the example that we just worked out. So the next thing then is a curl operator. So we have taken the operator, operated it on a scalar field, right? We operated it on a scalar field, and from this we got the gradient, which is a vector field. So that was gradient, which gives rise to vector field, and this gradient points in the direction of maximum increase, and its magnitude gives you the rate of increase. Then we took the same operator and did a dot product with another vector, and that's what we call as the divergence, which tells you how the flow is, whether there is an outward flow or an inward flow. Now what we are going to do is we're going to do a cross product. This is what we call as curl. And like how its name sounds, it is going to look at how much the field is curling around. It's not talking about a macroscopic curl. It is rather talking about, if you stay at one point, how that microscopic curl at that point is. So we're going to look into what this means. We're now going to look at curl. So like how we did cross product with a matrix determinant, it's very similar here. We know what this del operator is, and we know what A is. So curl of A then would be simply the determinant of, you have the unit vectors x, y, z, and then you have dou by dou x, dou by dou y, dou by dou z, and then you have ax, ay, and az. The determinant of this gives you the curl, right? So you can write the components. For example, if I want to write the x component, I'm not going to write out all the components. I'm just going to write out the x component. So then I would have dou az by dou y minus dou by dou z of ay. Right? You can do the other components. So the result of this is also a vector. Right? The result of a gradient operator operating on a scalar field is a vector field. The curl gives you a vector, and the divergence gives you a number, the scalar. right? So each of these are giving, basically they're describing how a vector field is. You can generate a vector field, you can look at the direction along which there is maximum increase using the gradient, and you can look at how the field is diverging, whether there's an outward flow or an inward flow using the divergence, and curl tells you how the field is curling around. So to see what curl is, let's do an example. Let's take a vector. So we're going to do an example here. So the example is minus yx and x along y. This is the vector. So if we want to do the curl of this vector, then we're going to do x, y, z. This is the operator, dou by dou x, dou by dou y, and dou by dou z. Along x I have negative y, along y I have x, and along z I have 0. So then I'm going to get along the x direction, I'm going to get dou by y of 0 is 0, dou by dou z of z is 0, I'm going to get 0, and along the y direction I'm going to get dou by dou z acting on y is 0, and this is also 0, so I get 0. And finally, if I take along the z direction, then I get along the z direction I get dou by dou x of x minus dou by dou y of minus y. So then I get z, dou by x of x is 1 minus minus 1, or I get plus 2z. So notice something here, the vector field is along x and y directions, and the curl of that vector field is pointing along the z direction. What does this mean? Let's go back to the graphical representation. Let's go to the vector field representation and look at how these vectors look like. So let's go back here. So we can look at this vector field. So this is going to be minus y along x-axis, and this is going to be x along y-axis, and there's nothing along z. So now if you look at this, you can see how the field is curling around. I had a good orientation right there. So you can see how the field is curling around. So if you go along with the right hand thumb rule, right, if you curl your fingers along the direction of the curl, the thumb is pointing towards the direction of curl. So this is what the vector field looks like, and it is curling. If you curl your fingers along the direction of the curl, then your thumb points along the direction of the curl of this vector field, right? So that's what we have here, right? So if we curl along x and y planes, we get the thumb pointing up to z, right? Again, like the case with the divergence, even in case of curl, one can be misled. So now let's do a simple example where you can see how there can be no divergence. How there can be no curl. Minus yx plus xy. So this is essentially vector A, divided by, I'm adding a factor to balance it out, x squared plus y squared to the power 3 by 2, right? And then let's see what this looks like. Let's go back to the thing here. So what we're doing is we're going to do x squared plus y squared to the power 3 by 2 x squared plus y squared whole to the power 3 by 2. just going to copy this and paste it here, right? So then, you can see that still it looks like it has a curl, but notice that unlike the previous example, the length of the arrows is changing, right? So it may look like there is a curl here. So let's compute to see whether there is a curl or not here. So let's do that. Go back to the PowerPoint. So we want to calculate curl of B. So we write down this x, y, z, dou by dou x, dou by dou y, dou by dou z, and I have x minus y divided by x squared plus y squared whole to the power 3 by 2. Then I have x divided by x squared plus y squared to the power 3 by 2, and then I have 0 here, right? So let's look at the z part would obviously be 0 because the z part would not be 0. So let's look at the other parts, right? So if I take the z, then I have dou by dou x of x over x squared plus y squared whole to the power 3 by 2 minus dou by dou y of minus y x squared plus y squared 3 by 2, right? So if I want to do dou by dou x of x by x squared plus y squared by 3 by 2, I'm going to use the quotient rule again, right? So that is if I have d by dx of f over g, both functions of x, then f prime g minus g prime f by g squared, right? So I'm going to do that here. So f prime would be 1, and I would have x squared plus y squared to the power 3 by 2 minus g prime would be, I would get 3 by 2 times 2x and x squared plus y squared to the power half divided by x squared plus y squared whole cubed, because we're squaring it. So now if I pull out from here x squared plus y squared to the power half, x squared plus y squared to the power half, then I would have x squared plus y squared minus, I would get a square here because I have f is x, so I would get minus 3x squared, right? And here I get x squared plus y squared whole cube, right? So if you write this, I would get half minus 3, so then that would give me 1 by 2, so that's 1 minus 6 or minus 5 by 2, or that would give me x squared, so it would give me this x squared plus y squared, so x squared would give me minus 2x squared plus y squared divided by x squared plus y squared to the power 5 by 2, right? So then I can do something similar with y, but the sign has to change. So I would get z minus 2x squared plus y squared divided by x squared plus y squared to the power 5 by 2 minus, right? I can put this minus sign here, so I get a plus, right? And I do dou by dou y, so then I would get minus 2y squared plus x squared, right, divided by x squared plus y squared to the power 5 by 2 along the direction z. So the denominator is the same, right? And so you get basically along z direction, you get minus 2x squared plus x squared, so you get minus x squared minus y squared divided by x squared plus y squared whole to the power 5 by 2. This is only along the z direction, right? We still have to do along x and y, right? So if I do along x-axis, I get this is 0, and this is also 0. There is nothing there. Dou by dou z. If I do along the y-axis, then also I get 0, right? Because dou by dou x of 0 gives me 0, and dou by dou z of this would give me 0 because there is no z here, right? So then I see that now this has a non-negative curl, right? So instead of doing x squared plus y squared only in 2 dimensions, what if we have another vector field that looks like minus y along x plus x along y. Now in the denominator, instead of it being 0, what if I have x squared plus y squared plus z squared? So instead of having z to be 0 in the denominator, I'm adding this. So how would this look like, right? So this would be on homework 2. So you can plot it and see whether there is a curl or not. So let's you can quickly do that using the derivative calculator. Now the z, like in the previous problem, because you have a z square here, right? You have a z square here. The dou by dou z derivative would not cancel out, right? So you can see what that is, and you can use grapher to see how the vector field looks like, right? So that's about curl and divergence. So next we can get into product rules, right? So now we have introduced this new operator, right? Gradient. So if I look at the types of products, if I have 2 functions f and g, which are scalar functions, I can multiply these 2 to get a scalar, right? Or another way is, if I have 2 vectors, I can take a dot product. That would also give me a scalar. But if I multiply a scalar with a vector, I get a vector. And if I do the cross product, also I get vector. So based on this, there are different product rules that you can write down, right? For example, you can write, if I have to take gradient of fg, then I do f of gradient g plus g of gradient f. That's one product rule, right? The second one is, if I want to take the gradient of a dot b, right, then that is a little more extensive, and this would be one of the homework problems to show. It would be a cross curl b plus b cross curl a, right? Plus I think a dot the gradient b plus b dot the gradient a. So these product rules, you don't have to remember them, you don't have to memorize them. They would be given to you on any exam where you need them, but it is good to do an exercise to prove them. So you will see some of these product rules. I will ask questions on homework, and we will discuss that also in a Zoom session, so that you can see what these product rules are. So from these product rules, we can also look at various types of second derivatives, right? So by taking a scalar field, for example, temperature along xyz, we took a scalar field as input, and we operated gradient, and then we got a vector field, right? So now I can take the divergence of this vector field, right? Because I can see how the change is diverging, right? How the gradient is diverging. So I can take divergence of gradient, right? Similarly, because the gradient is a vector, I can also take the curl of the gradient, right? And the divergence itself is a number, right? When I do divergence of A, it gives me a scalar number, and this is a scalar field. So it can be an input for the gradient operator. So I can do gradient of divergence, right? And then I can do divergence of curl, because divergence is acting on a vector and curl is a vector. So I can do divergence of curl. or I can do curl of curl, because curl of curl is also curl is a vector, so I can operate curl on this. So I can do curl of curl. So these are 5 different types of second derivatives that there can be. Again, going over that, T is a scalar field, gradient T gives you a vector, dot product or the divergence is a scalar. So you can take the divergence of the vector field or curl of the vector field, which comes from gradient, or you can take the gradient of the dot product, the divergence, or the divergence of the curl, or the curl of the curl, right? So you can prove that, for example, the first one, right? If I take gradient, or if I take divergence of gradient T, that is very simple to see. So that would be dou by dou x along x plus dou by dou y along y plus dou by dou z along z, okay, dotted with gradient of T. So the gradient of T would be dou T by dou x, right, along x, right, plus dou T by dou y along y plus dou T by dou z along z. So now if you do this dot product, again this is a dot product because you're doing the divergence, we're looking at number 1 here. So then I would get dou by dou x of dou T by dou x. I would get a double derivative, dou square T by dou x squared, plus then I get dou square y by dou y squared, same thing for z, right? So we call this, instead of writing as this, we can call this as del square T, right? And this del square is called the Laplacian of it. Right? So Laplacian of a scalar, if I take delta square of T, I get back a scalar. Why? Because what is Laplacian? It is, you're taking the divergence of gradient. Right? So if I have a scalar field T, first I do the gradient, this produces a vector, this is a vector when I do gradient, and I'm taking the gradient of this, right? Sorry, I'm doing the divergence of this gradient. So this is a dot product, so this is again a scalar. So we started with T, which is a scalar field, and when I do the Laplacian, that is the divergence of the gradient, that is the Laplacian of a scalar field, gives me scalar, right? But here you can also do the Laplacian. We'll study in later detail that we can do Laplacian on a vector as well, because we can have Laplacian as a vector operator as dou by dou x plus dou by dou y square y plus dou by dou z square z, right? We can also define so we can also define Laplacian of a vector as del square v, which we will look at it later. But going back, we are also going to look at now curl of gradient T, right? So curl of gradient T, if we want to look at curl of gradient T, we have curl of gradient T. This is also easy enough to do. So curl of gradient T would be x, y, and z, and the curl is dou by dou x, dou by dou y, dou by dou z, and here you have dt by dx, dt by dy, and dt by dz. So we'll see just for one component. For example, if I just look at the x component, right, then I would have this, right, dou by dou y of dou t by dou z minus dou by dou z of dou t by dou y. So if I interchange these variables, these things are the same, so they cancel out, and curl of a gradient is always 0, right? So that's how you show that. Okay, so similarly we can also show that divergence of curl is also 0, right? That's again simple enough to show, and that will be on the homework. And similarly, when you take So we did the first two, these two, right? And then we can look at these two, right? The divergence of a curl is always, again, we'll see that it is 0, and that will be again a part of homework 2, and we will do this also as a part of homework 2. So this covers all the things we need in terms of differential calculus, right? We'll talk about the Laplacian of a vector later in more detail. I have not given complete details of the Laplacian as for the vector fields, but I have only looked at Laplacian for scalar fields here. We'll talk about Laplacian for vector fields later in more greater detail. But for now, what we have done is we have looked at what gradient is, what divergence is, what curl is. We have done some examples of these divergence and curl. And then we have looked at second derivatives and some product rules, which you will get more understanding through homework and some more homework problems. But this sets up the the mathematics that we need to study electromagnetic fields. And in the next lecture, we will talk about integral calculus, and we'll talk about some interesting things like Green's theorem, and look at the divergence and the fundamental theorem of gradients and the fundamental theorem of divergences, so on and so forth. And we will try to complete chapter 1 in the next 2 lectures. Thank you.